I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
So welcome to episode number 61 of the Physics Matter colloquial series. So my name is Christine Darf and I work at the European Spallation Source in Sweden, and I'm the former chair of the Forum of International Physics, the FIP, at the American Physical Society. So which is also proudly supporting this series. So today, I'm pleased as well to welcome in our panelists, so Alan Hertz from Los Alamos National Laboratory and Johnny Mella from International Center of Theoretical Physics and the well-known, so the ICTP in Trieste, and he's also a member of the International Year of Quantum Committee. So both have been outstanding colleagues and former FIP chair as well. So our Physics Matter colloquium series invite anyone who wants to understand how physics impacts our world. So for 5 years, so we have traveled through topics spanning into research infrastructure, discovery, accelerator, and international partnership. Those partnerships are essential for this society. So you are very welcome to visit our webpage and to watch any of our 60 inspiring recordings. So join us and we continue this CO2 neutral adventure in science. So this fall, so our series focused on Africa and will return there next March after the closing of the UN International Year of Quantum Science and Technology in Ghana. So with, for instance, last October, we had the honor of having Professor Yassera, who reported the building of Africa quantum future to strengthen the research and innovation capacity. So to conclude 2025, now we are delighted to welcome Professor Ana María Cetto to reflect the International Year of Quantum and to celebrate this outstanding achievement in science. So Ana María Cetto is a leading Mexican physicist specializing in the foundation of quantum physics. She holds degrees from Harvard and the National Autonomous University of Mexico, the UNAM, and has served in major leadership roles, including director of the Faculty of Science at the UNAM, president of the Mexican Physical Society, the International Science Council, Secretary General, and the founder of the LaTeX. So she has published over 150 papers and 25 books and has received distinction at the UNESCO, as for instance, the UNESCO Kalinga Prize in 23, the Oganesson Prize in 24, the AIP Tail Medal in 25, and and far from being the last prize, I hope that you will also be awarded for. She is also co-recipient of both the 1995 Pudwash and the 1995 IAEA Nobel Prize for Peace. So we are very honored to have you with us today. So in the meantime, so you can prepare your question that you can address directly after the presentation, which would last about 40 minutes. And we will give possibility for writing as well those questions or giving you the microphone to ask your question now. So in the meantime, so Professor Cetto, so the floor is yours.
Thank you very much. Thank you very much, Christine, and thank you also, Claudia, if she's there, Claudia Fraciola from the American Physical Society, for inviting me to give this talk which is indeed the last of the Physics Matters webinar series dedicated this year to the International Year of Quantum 2025. As we approach the end of the year 2025, I think it is time to start summing up and reflecting on what the IYQ has meant for quantum science and technology. It is time to take stock and look ahead. The range and number of activities throughout the year have been so broad and diverse that assessing their full impact would be premature. I would rather leave that to the official closing ceremony of the IYQ, which, as Christine has just mentioned, is planned to take place in Ghana in February of next year. However, it is not too early to mention some significant experiences. So I will try to share my screen. You tell me if it works.
And that works. Thank you.
Okay, fine, yes. So, well, as scientists, we are used to believing in the importance of our own field of research. The International Union of Pure and Applied Physics General Assembly number 30 from October 2021 decided to promote an international year dedicated to quantum science with support from over 30 national and international physics-related organizations. And this demonstrates our community's strong belief in the importance of quantum science. On the other hand, given our experience with the general underappreciation of science by decision makers and the public outside the scientific community, we naturally anticipated that bringing the IUPAP initiative to fruition would be an uphill battle. Well, I'm happy to say that this has not been the case. You may be aware that international years can only be proclaimed by the UN General Assembly and only after prior endorsement by a UN agency. In this case, the endorsement came from UNESCO, as the theme falls within their domain of expertise. And thanks to the close collaboration of the Permanent Delegation of Mexico and a small IYQ 2025 steering committee with John Dudley, Joe Niemela, who is present here, and Kamal Asri from the UNESCO Secretariat, the UNESCO General Conference adopted a resolution in November 2023 recommending that the UN proclaim the IYQ 2025 by acclamation, that is, without discussion of a vote, which is not usual. The permanent mission of Ghana to the UN then took the lead in New York. As a result, in June 2025, the UN General Assembly decided to proclaim the 2025 as the International Year of Quantum Science and Technology, with the support of over 70 countries. The lobbying process at both UNESCO and the UN was stimulating in itself. You know, in general, ambassadors and other member states officials, well, were quite unaware of quantum science and its impact on modern life. To this, one should add, let's say, traditional resistance among them and their governments to support international year initiatives, on the argument that they may entail costs, both political and financial, with no returns, which is not true, but well. However, this resistance dissolved quickly through a series of awareness-raising and informational meetings, which sparked their interest and garnered their support for our cause. The process leading to the UN decision and the decision itself can be already considered an achievement of the scientific and diplomatic communities in putting quantum science and technology on the international agenda. Throughout the year, thousands of activities have taken place at all levels around the globe. The map displayed on this slide gives a good idea of the geographical distribution and variety of events. although we are aware that not all events taking place are actually registered. We will save the statistics for a more opportune time once they have been compiled by the IYQ office convened by UNESCO and the American Physical Society. For now, I would like to briefly discuss the long-term impact that we can already foresee or expect. The main purpose of the IYQ, which was to help raise public awareness of the importance and impact of quantum science and applications on all aspects of life, has certainly been achieved. It is extremely stimulating to see, in particular, the breadth of initiatives, including public-private partnerships in areas such as renewable energy, precision measurements, quantum computing and information, photonics, nanotechnologies, and semiconductors. Several institutions have been created this year that engage in quantum innovations in these fields. Quantum physics is now being taught in a more substantial way in some universities. Not all of them, I must say. Emerging issues such as quantum legal frameworks and global quantum governance are being addressed. As I speak, for instance, ASEAN state members are gathered in a summit in Malaysia to discuss the quantum ecosystem within the region, and the Pakistan Quantum Day celebrates Abdul Salam's groundbreaking contributions to science. While students at the Museum of Quantum Realities at the University of Illinois explore quantum science through the arts. Tomorrow, it's the closing chapter of Africa's quantum community, where women leading in quantum from the continent and diaspora take the stage to define what comes next. Myriad research papers on quantum science and applications have been published, as well as textbooks, monographs, and public outreach material, like this book. We are celebrating the first 100 years of modern quantum mechanics, and it has already transformed our understanding of nature at the most elemental levels, including atoms and subatomic particles. Thanks to quantum science, we now understand why the sun shines, how magnets work, how atoms from chemical bonds, how galaxies formed in the universe. Quantum science has been central to some of the most significant technological advancements of the past century, of the past 100 years, and it will continue to play a pivotal role in shaping the future. It is actually difficult to envision what kind of future this will be. We can extrapolate a few years, perhaps, into the future and imagine a host of new applications that will likely lead to technological products and processes, quantum-based technologies that continue to impact our lives, our jobs, our habits. We can further use our imagination to picture a future filled with groundbreaking and as yet unforeseen applications, each one a potential game changer. These innovations will likely emerge from research labs where intense competition drives developers and entrepreneurs to push the boundaries of what is possible. But now I would like to invite you to imagine quantum mechanics, the basis of all quantum science and technology, as a sturdy trunk of a century-old tree that adds a new ring each year. As the tree grows, it develops new branches. Some branches are thick and short, while others are thin and long, with many ramifications. The major areas that emerged after 1925, nuclear physics, particle physics, quantum field theory, molecular physics, quantum statistics, quantum optics, material science, quantum information, and so on. Those are the side trunks and thicker branches of this tree. Others, such as quantum gravity and quantum computing, are striving to develop. The quantum tree continues to grow and produce flowers and fruit As with every tree, new branches and twigs may appear with the changing of the seasons, while some may dry up or twist, like with any genealogical tree. This is evolution. When fruits fall to the ground, their seeds may germinate and grow into new trees. We are thrilled that our quantum tree is bearing so much fruit. We want even more. Needless to say, a tree that wants to grow higher must extend its roots into the earth. And to keep bearing fruits, the tree needs a healthy root. However, in our excitement, we have overlooked the tree's roots and the soil that nourishes them. The basic questions that sparked heated debates among quantum pioneers relating to the deep meaning of the nascent formalism remain largely unanswered and are far from enjoying a consensus explanation. Instead, the physics community has displayed considerable creativity and imagination in proposing a variety of interpretations lacking a physical basis, some of which even contradict among themselves and contradict well-established physical principles. Is there instantaneous transmission of information? Can a particle be in two places or two states at the same time? Or does it transform into a wave to later recover its particle identity? Can there be instantaneous non-local collapse? Do we need multiple universes? These confusing and puzzling messages, once conveyed to the general public, have naturally given way to all sorts of pseudo-scientific and miraculous so-called explanations in quantum disguise. To some extent, alas limited, I should say, the IYQ has helped raise awareness of the confusion and lack of consensus that still prevail 1 century after the birth of quantum formalism and its core elements. One fortunate contribution in this regard is a global survey of physicists about quantum foundational issues, which was conducted by Nature and reported on in July this year. The responses to the survey reveal a persistent tension between the so-called realist views, which seek an objective, visualizable account of quantum phenomena, and the so-called epistemic views that regard the formalism as merely a tool for organizing our knowledge, calculating and predicting measurement outcomes. Interestingly, only 5% of the 1,100 people who responded to the Nature survey expressed full confidence in the Copenhagen interpretation, which is still prevalent in textbooks and laboratories. Further divisions were revealed over whether the wave function is a physical entity, a mere calculational device, or a subjective reflection of belief. These different views are found even among the Nobel Prize-winning physicists who work on topics related to the quantum foundations. They don't come to an agreement. The lack of agreement on such central feature underscores the theoretical fragility underlying quantum mechanics, the roots of the quantum tree. The various interpretations that prevail essentially aim to fill the gaps created by the theory's ontological incompleteness, which is evident in the absence of a physical agent of quantum phenomena. While the theory describes the statistical outcomes of measurements with great precision, it does not explain the mechanisms behind them. The concept of causality has largely been abandoned, if it was ever there, in favor of operational prescriptions, and as a result, quantum theory works impressively in practice, but remains conceptually opaque. This underscores the need for serious fundamental theoretical and experimental research on its physical underpinnings. Notably, the majority of respondents to the Nature survey believe that quantum theory will eventually be replaced, at least partially, by a more complete framework. And 85% agree that attempts to interpret the theory in intuitive or physical terms are valuable. This willingness to explore alternatives reflects the intellectual vitality of the field, but also underscores the inadequacy of current approaches. Therefore, rather than multiplying interpretations or continuing to debate them, we should pursue a deeper physical understanding of quantum phenomena. Some colleagues and I have already been pursuing this line of research for some time, decades already, with stimulating results. One promising approach is the theory called stochastic electrodynamics, or SED for short, a classical theory augmented by a random electromagnetic background field, the real vacuum or zero-point field, which was discovered by Max Planck as early as 1911, 1912. This framework restores causality and locality by explaining quantum behavior as the statistical response of particles to this omnipresent background field. In stochastic electrodynamics, particles acquire wave-like properties not from intrinsic duality, but from their interaction with the vacuum field. Quantum fluctuations, interference patterns, and entanglement emerge from this permanent interaction without resorting to non-local influences or to observer-dependent realities. This approach is not merely mechanical, it is not simply a quantum mechanics, but it is electrodynamic because the field is permanently interacting with the electromagnetic radiation field. It would be pretentious to claim that stochastic electrodynamics is the final word. However, the theory does offer a coherent picture of microphysical processes based on physical fields and forces. Importantly, stochastic electrodynamics doesn't abandon quantum formalism. Rather, it reframes it as what it actually is. It is an effective theory, a coarse-grained statistical summary of deeper dynamics. As shown in this slide, causality is recovered for physics, as it is in the rest of physics and in the rest of science. The description afforded by quantum mechanics is indeterministic, which is no surprise. In fact, it is no problem either. We also have a description of Brownian motion, which is indeterministic, which doesn't mean that it doesn't have a cause. It is the description that is not deterministic. And there, that is what gives rise to the famous Heisenberg inequalities. Non-commutativity acquires a physical sense because the commutator, the basic commutator of quantum mechanics emerges from the interaction of the particle with the radiation field. It actually expresses the non-commutativity of the X and P, which are the response functions of the particle to the field. They do not describe the trajectories, and that is why there is no phase space associated with the operators X and P. The background field correlates identical particles. The particles are attached or interact with the same modes of the field, and thus those field modes are the ones that correlate their behavior. And this is what gives rise to the apparent non-localities. Non-locality is not a feature of the reality itself, of the quantum reality. It is apparent, it is part of the description. In this way, stochastic electrodynamics completes the puzzle with the missing piece, which is the radiation field with which the particles are always interacting. All atomic particles are electromagnetic, in fact, or nuclear particles as well. The perspectives allows us to retain the successes of quantum mechanics thus, and explains its origins, and situates quantum mechanics within the broader physical context. It's not another physics, it's the same physics, but it describes particularly quantum mechanical phenomena, which are phenomena characteristic of microsystems where correlations and coherence are essential. And even more importantly, it opens the door to new, deeper realms of physics yet to be explored. Well, here are some useful references. The first reference mentioned here by Trevor Marshall is the first paper that was published in which the zero-point radiation field is taken seriously. Although it had been mentioned also seriously by Nernst in 1916 as the possible source of explanation of the stability of atoms, it was not taken into account until 1963 when Marshall rediscovered the zero-point radiation field and took it seriously. A number of books and many papers have been published since then, and I would like to use this occasion to draw your attention to a textbook which is about to appear exactly in 1 week from now, which we have prepared recently precisely with the purpose of showing to university students, both under and graduate students, that quantum mechanics can be understood, that it can be explained, and that there is a physical explanation to it. So we consider that there is a lot of future for quantum mechanics, but we have to pay attention to its roots so that the quantum tree continues to grow healthily. Thank you very much for your attention.
Thank you very much, Professor Cetto. It was really enlightening to see all those different capacities as well that quantum can have. So everyone can feel free to raise your hand or to ask questions in written as well in the Q&A. So we have already a few questions that arise. So maybe we'll start by those questions online. So we have Harrison Prosper, who was asking about so how does the stochastic electrodynamics evade the idea that hidden variable theories are not viable as quantum proxy? Interesting.
I did not get every word of your question. I know it has to do with hidden variables, but if you can repeat it so that I can also give a proper answer.
Very good. So stochastic electrodynamics evade the idea that hidden variable theory are not viable as quantum proxies, isn't it? So how does? Why and how?
Well, yes, we are not worried about the hidden variables because, as I said, for instance, we already have in the case of Brownian motion, there are lots of variables that are hidden variables in the description, which doesn't mean that we don't have a cause for the Brownian motion, which is the permanent impact of the molecules of water on the grain of pollen, let's say, no? Originally, let's say, the original Brownian motion. In this regard, also, you have the background field, which is permanently interacting with the electrons, and we are not in a capacity to describe the instantaneous position and momentum of every particle and the phases of the waves of the electromagnetic modes that are interacting with the particles. But it would be pretentious and it would make no sense to try to describe them. So the description is necessarily indeterministic. we have also worked on the issue specifically of the of Bell's theorem in all its variants, no, including the CHSH, the Clauser-Horn Shimony-Holt version, which is the most popular one. And we have shown that this poses no problem if one takes into account that those different versions of Bell's theorem, of Bell's inequality, let's say, of Bell inequalities, have actually a hidden super hypothesis, which is normally not made explicit, which is that you can, thinking already in terms of measurements to make it more visualizable, let's say, that you can use the same realization of the ensemble of hidden variables for the different settings, the different experimental settings. However, the variables that actually intervene in each series of experiments are statistically independent from each other. So every time you change the setting and you perform a new, let's say, run of experiments, you are using a set of variables which have the same distribution, but it is a different realization of that ensemble of realizations, of possibilities. So in theoretical terms, this means that you have different partitions of your ensemble of possibilities, that is, of your probability space. And you cannot mix the results obtained with one partition and with the other one. That is, in the derivation of a Bell-type inequality, you cannot put all the terms under the same integral, let's say, integrate of the same realization of hidden variables, because the hidden variables each time respond to a different set of realizations. And this is our way of seeing it. So we have no problem with there is no non-locality. Realism is preserved, locality is preserved, no problem. What the Bell-type theorem is telling us is that it is valid whenever you have the possibility of having the same set of realizations for different experiments, which is not true in the case of quantum mechanics in particular. Yeah. I hope I have. It's a very delicate issue, very tricky. There has many thousands of papers have been published, so it's not easy. And there is much dogma already. There's already a mindset that goes along with the idea that the world is no local, or other similar conclusions. Yeah, but there have been other let's say, approaches to the problem that come to the same conclusion, particularly from the point of view of probability theory, extending the Kolmogorov probability theory and showing that there is no problem with quantum mechanics, that reality, the experiments don't have to violate quantum mechanics. Quantum mechanics has not been violated experimentally, not with the Bell-type experiments, not in other instances. Quantum mechanics works very well. It is true. It doesn't have to be put to test with Bell tests. Thank you.
Yeah, Thank you for this beautiful answer, indeed, as Harry Prosper is just answering. So if you don't mind maybe to stop sharing like this, we can also
Yes.
do better. And indeed, so the second question from so Dimitri Burikov, so is maybe part of what you already answered, but he's asking also, so can the stochastic electrodynamics explain as well this Bell's theorems? So maybe to elaborate a bit on that.
Well, I think to go perhaps a bit further to what I've already said, because I've given a general answer that does not have to do specifically with stochastic electrodynamics, but the fact that we are dealing with a stochastic theory, that we have shown, in fact, we had shown previously, before working with stochastic electrodynamics, we had shown that quantum mechanics is a stochastic theory. And it is not Brownian motion. It is different from Brownian motion. And we established the differences between Brownian motion, which is a classical stochastic theory, and stochastic and quantum mechanics, which is not the same kind of theory, stochastic theory, because the Schrödinger description is reversible in contrast with Brownian motion. And it has other features. It has these wave-like features which are not present in the case of Brownian motion, etc. But it is stochastic. It is essentially stochastic. It's essentially stochastic, not just because of the thermal fluctuations, but because there is also a more fundamental, a more fine-grained stochasticity, let's say, that is linked to this permanent interaction with the wave field, and the phases of the wave field are absolutely they're random, the phases of the wave modes that interact with the particle, and are statistically independent, the phases of the different modes, because the modes don't interact among each other. So and that is the cause, the element of, that's how the stochasticity comes into the picture, but only Planck's constant, and that is what makes it interesting, because this background field carries with it Planck's constant. So, and that's what also gives rise even to the basic commutator, to the canonical commutator. So it is a coherent picture. As I said, maybe it's not, I wouldn't say, as Heisenberg and other founders said, that was the last word and quantum mechanics is there to stay. Yes, quantum mechanics works well, very well. It has been tremendously successful, but it's still growing, and we still have much to explore to really understand what is behind it. And the stochasticity is essential. When you ask the artificial intelligence what's the cause of the stochasticity in quantum mechanics, the answer you get is, the cause is the Heisenberg principle. No, it's the other way around. I mean, the principles, the postulates of quantum mechanics were introduced because no attention was paid to the cause of it. But now we are in a position, after 100 years, to get a better understanding what is behind. And it's not just a philosophical question. It will help us also go beyond quantum mechanics and beyond quantum physics to other realms. It broadens our understanding of our physical world more in general.
So really a growing tree, and with many, many branches. And
yes.
As you said, the cause. So excellent. So we have as well another question from Javier Ho, who is asking, so what about quantum physics of electrically neutral entity? So should any claim for fundamental aspect of quantum mechanics should be able to deal without the electrodynamics and the electrical charge?
Yes, that is this is a classical question, I must say. It is an important question, and the fact is that I admit I did not mention at all that Of course, stochastic electrodynamics deals with any particle that has an electromagnetic nature. And all atomic and subatomic particles are electromagnetic in nature. So that means that the electromagnetic radiation field is sufficient to understand quantum phenomena, the origin, the emergence of quantum phenomena at that level. But, and you can even understand entanglement, for instance. But now, for instance, it's very interesting to see that some papers are being published that question whether there is something like quantum entanglement at the gravitational scale, on the gravitational scale. And that's an interesting question. There is already a debate whether that entanglement is quantum or is classical. Well, what is quantum and what is classical, you may ask, no? But for us, for me in particular, an entanglement at that scale would be a very natural phenomenon. Wherever you have a wave field that interacts with matter, you may envisage the emergence of entanglement as well. So that gives us already, let's say, a certain advantage in understanding how quantum-like phenomena can also be present at other scales in the universe, or in the physical universe.
Thanks a lot for the answer. So we have then another question. So by Oliver Massot, who is asking, so how does stochastic electrodynamics explain the particle spin?
Mm-hmm. Yes, we have published several papers on this issue some years ago, and the emergence of spin on a, let's say, still a phenomenological level or semi-phenomenological level is related to the angular momentum of 1/2 h bar of the 0-point field radiation modes. As you can see in the classical quantum optics books by Mandel, etc., the 0-point field modes have an angular momentum of 1/2 h bar. And you can make a rigorous derivation of the angular momentum acquired by particles that are interacting with the field. Why some acquire half spin, why some acquire, why some are fermions and why some are bosons is another question. And that question we have approached more recently, and we have indeed established a linkage, a direct linkage between the modes of interaction of fermions and bosons with the background field and the spin statistics theorem. No, that is to say, in a way, we derive the spin statistics theorem as a result of the way the particles attach themselves to the modes when they are interacting, when equal particles are interacting with the same background field, let's say, when they form part of one system and share the field modes among them.
Very good.
Now, the internal structure, let's say the internal motion that gives rise to the spin that is related, let's say, to what was discovered by Schrödinger described by Schrödinger as a Zitterbewegung, and then later appears in the Dirac equation. That is something still to be studied. That is an open question. What is this internal motion? There are some very interesting recent attempts to to describe, to understand that internal motion, but there is no definite answer yet.
So still under research, and maybe some
Yes.
dimension as well, who knows? Yeah.
Yes.
So another question from Eleni Petrakou, who is asking, can you say a few words about whether the experimental check, on this stochastic electromagnetics, have been proposed?
Yes. I think we are not so far from that. And I will briefly explain why. In our understanding of quantum mechanics as a stochastic process, we have learned that the current quantum mechanics is a coarse-grained description, just like Brownian motion is a coarse-grained description. No? Well, it's statistics. This coarse-grained description means that there is a time interval that is not infinitesimal, that has a certain size, and the size of this time interval, or the description, this coarse-graining time interval, is of the order of 10 to the minus 18 seconds. Probably, if we want to be optimistic, 10 to minus 17, but not more than that.
We need better instruments. So this is also...
Exactly. But, well, experimental physics is going there, no?
What about neutron source, and potentially as well trying to understand how with photon and neutron we can have...
Yes. Also in extreme conditions, maybe, no? One problem with this trying to find an experimental, let's say, a test of the SED predictions is that you cannot empty the space from the 0-point field, because all matter, of course, it owes its stability to that field. The stability of the ground state of matter is due simply to the 0-point field, no? Like the harmonic oscillator, which also has a 0-point energy of 1/2 h omega, no? But all matter is linked, then is stable thanks to this field. So how can you cannot take it out? You cannot build a Faraday cage to expel you can. With Casimir, let's say, you can produce Casimir effect. Yes. Well, the Casimir effect, in fact, is an outcome of this, let's say, effective force due to the that you are expelling a few modes of the field of the background field within the cavity, no. But you can't not expel all modes. You cannot, because then there is no matter that is there. No? So that is a contradiction, and that makes it more difficult to find let's say an easy way, a more or less feasible way to test the theory. We have to think of some extreme condition, or wait until the experiments can go further in shortening the times, no? Yes, observing phenomena at shorter times, but we're not so far anymore.
We're not that far, indeed, with Anne.
No, not that far. Thanks to Anne Louvier, among others, yes.
There's so much, it really opens a lot of frontiers, so very exciting time.
Yes. No, there's a lot of frontier science there. One can think, quantum mechanics is already there. We are using it with much success. Yes, but there's also, underneath, there is still frontier science to be explored here.
Exactly. Frontier. So now as well with Alan, so thanks a lot for having waited. So you want to ask your question before we come back to the written?
Well, absolutely. First, a comment. It's a fascinating topic. I think it was economist Robert Sokolov who said that 50% of the U.S. gross domestic product relies on quantum mechanics. And Ana Maria, you should be congratulated for helping out in the productivity of the human race, because you're producing a nice Christmas book that goes on my Christmas list.
Thank you.
So now I'm wondering, I had been, as a layman in quantum mechanics, I've been taught to think of the Higgs field as the prevailing background field. Are you telling me that that should be considered to be a stochastic field as well?
Well, the stochasticity, in my view, comes from the interaction of the field with the rest, with matter. No, it's because of what I said. I mean, the good thing about the field is that you can always think of decomposing it. No, in the case of the radiation field, we always think in terms of Fourier components. No. Mm-hmm. And they have an amplitude and they have a phase, and the phase is what is absolutely out of control always. You don't have a control over phase. And interestingly, only when, for instance, you, as I mentioned earlier on, when you have a system with two identical particles that interact through the field mode, then the phase difference becomes either half phase or 2 pi or pi, no? But every mode has its own phase, which is statistically independent of others. So that is where stochasticity comes in. And I can imagine that in other fields, in other cases with other fields, the stochasticity will have a similar origin, let's say.
Okay,
so it's not a randomness; it's an essential feature of nature. I mean, in Einstein's words, it's not the God. Let's say nature plays with dice. No, it is the combination that brings that produces this. This stochasticity. It's a result of the interaction.
I think I get
like
it.
In Brownian motion. I come always back to Brownian motion because it's much more easy to understand.
And yet, it's if the masses of particles come from the Higgs field, then is that also a stochastic variable, the mass?
Well, there must be some, yes, but that is already another scale. I would not dare extrapolating so readily.
Yeah.
Yes.
Well, I'll have to get your book and see if.
Okay. Yes. By the way, my husband and I, Luis de la Peña, because we are co-authors of this book, have decided to pay the Cambridge University Press so that it can be put in what is called gold open access, that is free open access online, so that the students can use it freely without having to pay for it. But it is coming out on 1 week from now, also in print on paper. Yeah.
Good for you.
So in time for Christmas.
For Christmas, yes.
Good. And indeed, speaking about the deterministic part as well, the case of the cow, the theory of cow as well, maybe, and with indeed because in September, so we had a Professor Wafo from Cameroon who was presenting this non-linearity science as well, and the different. So indeed, speaking about the cow and this deterministic place, so do you feel that there would be indeed some potential field for new experimental proof of both? Because I think it's more theoretical for both.
Yes.
Where would you go? Which direction would you suggest?
Yes. Well, in fact, another thing we have discovered, and this this has been very enlightening for us, is that actually the quantum description, the quantum mechanical description, and this is especially clear in the case of the Heisenberg formalism, the so-called matrix formalism, is a linear response theory. It's the description of how atomic and molecular systems react linearly to the field, no? Response to the field. And the matrix elements of X and P are the response functions, just as Heisenberg had said in his original paper of 1925. That's very interesting, because he, even in the title of his paper, he's not saying it's a reinterpretation. He's saying it's a re-signification. It's a change of meaning of the variables. It's a new kinematics. And that's what it is. It's not the position and momentum variables. This is a response coefficients. No, that is what it is. So, but this is a linear response. If you are familiar with linear response theory, you will immediately realize that that's what it is. No? Now, what happens when you have a strong field, like the fields produced now with lasers? Well, what does quantum mechanics do? Oh, we add terms, we introduce perturbations, or we make the Schrödinger equation non-linear by adding a non-linear term, etc. Well, this is working in patches. I mean, what we need is a first principles theory to work with a system that does not respond linearly anymore. But this is not yet there. There is another area that needs to be worked in, explored, yes, which is quite complicated, but I mean, yes.
Maybe hidden variable. Maybe potential hidden variable. So something indeed in addition to.
Well, I would say I'm not concerned. I'm not worried by hidden variables. No, I would say we don't have yet the electrodynamics of particles interacting with nonlinear fields, with very intense fields. No, I mean, Maxwell's equations, the whole electrodynamic theory works very well, but it has worked very well under linear conditions with relatively fields of relatively low intensity. Actually, our thermal fields are of very, very low intensity. But the fields produced by during picoseconds at very high intensity by the new lasers, those produce highly nonlinear effects that are not properly described, not properly understood. And those need a different kind of fundamental theory that is not simply adding terms to a theory that has not been built considering these non-linearities, no? That is a linear response theory.
New field as well, potentially. I got. So we have another question also from Harrison Prosper, who is asking, so one would imagine that a fluctuating background field has some relationship to cosmological constants. Do you have any thoughts?
Yes. Yes. And we also published a paper on that long ago on the Dirac's large number hypothesis, and this is related to the Planck's constant, and we came to the conclusion that indeed, the whole universe is filled with this 0-point field and other 0-point fields. We are only concerned with the electromagnetic 0-point field, but we don't exclude the others. And electromagnetic particles are always, let's say, giving back to this field. There is let's say, a balance, no, sort of equilibrium field. That's the background field. I don't mean the microwave background. I mean the 0 point background, no, at zero temperature, not the thermal microwave background. And if it is true, as cosmologists say, that our universe is still expanding, that means that slowly, very slowly, the Planck's constant is changing also, no? Because there is no creation of new matter. And yes, the numbers fit. Let's say in this paper on the Dirac's large number hypothesis, we come to the conclusion that you may understand, you get a coherent picture of the relationship between Planck's constant and the other universal constants, the gravitational constant, the Hubble constant in particular.
Thanks a lot. So indeed, and then maybe indeed just before concluding, because also we recalled as well that you are the chair of the PUCVOS, so advisory board, and also the chair of the UN Independent Scientific Panel on the effect of nuclear war.
Yes.
So this other aspect, and to close also the year. So are there any advice as well for quantum physicists that you would like as well to hit for the next year?
Oh, well, of course, yes. If you ask, yes, this would be for me a very timely invitation to think of our colleagues, especially young colleagues, the young physicists, the students, to always bear in mind not only what they are doing, but for whom they are working, no? What is the purpose, no, of what they're doing? What can the impact of their work, of their results be, no? Whether it is for the benefit of humanity or whether it is not. And I think this is a question, well, it is a question that I've always had in mind since I began to study physics, and I think it's good that all physics students also bear that in mind, no? Yes, because, well, we can see that currently the world is not the safe place we would like it to be, and if we have a responsibility to work for a safer and a better world. Thank you.
Thank you very much. And indeed, so we want also to add to the comment from Matsushi, who is saying as well, agreeing with your idea that the nonlinear is an attachment. So he thinks that the quantum mechanics, we started in the Hilbert field, in the Hilbert space, can be nonlinear. So when multiplying, higher degrees tensor, still in this Hilbert field. So that's also, I think, an interesting comment. And everyone, thank you very much as well with this highlighting talk, and especially all those wonderful answers to the question that was raised by our audience and our panelists. So indeed,
thank you.
Thank you so much for being with us. And indeed, we'll hear more about the closing as well of this UN International Year of Quantum, and as well with my colleague. And we'll come back as well later on in Ghana. So after more direction towards neutron. So I will just mention the next presentation, which will be in January next year, the 29th of January, with a possibility to listen from our Professor Joseph Bevitt from Australia. So it will be very early in the morning for him. So he will describe the invisible and by showing case for the application of neutron in heritage research. So that will be possibility for everyone to hear more and ask as well question to him. So, and in the meantime, I think that we'll thank you once again, and we send the best greeting to everyone for finishing this end of 2025. So thank you.
Thank you, Christine. It has been a pleasure, and I appreciated very much the dialogue with you and with the audience. And thank you, Alan, for your questions and your comments, and thank you, Joe, for being here as always. A good company. Bye bye.
Stay tuned. Thank you,
Best
everyone.
wishes.
Bye.